All right, so today we'll start discussing the most important device that we'll cover in this course, and most probably the most important device that we should care about in our life at this point, right? As of now, all electronic devices that we are using, they're all built out of MOSFET, metal oxide semiconductor field effect transistor. So this is the most important device that you can think of at this stage of technology, right? Obviously, there might be new devices. This might get obsolete in 10 years. We don't know because things change. For example, BJTs were at some point the crown jewel of electronics, right? Everything used to be made out of BJT. Uh, Before that, vacuum tube. I mean, I haven't even seen a vacuum tube in my life, for example. It is so old. So similarly, things change, technologies move over to something new. But as of now, MOSFETs are the king. So without further ado, let's start discussing MOSFET. And as I discussed in the last class, I'll upload the second part of the BJT lecture. It's not optional, by the way. Please listen to it. And that's why I have a dedicated pseudo quiz on the BJT specifically, just to make sure that you still cover the content. You might be wondering, okay, if you don't care about it that much, why are you even covering it? The problem is, even without understanding the key concepts of BJT, you will probably not fully understand some other advanced concepts of MOSFET. Okay, so I want to make sure that you are still prepared to understand the MOSFET concept. Number two, there is another reason. When you get to 336, there will be BJT-based circuit analysis as well. So I don't want to leave you in the dark, like, oh, we didn't cover BJT. Does that make sense? So I'm going to cover it well in a more detailed fashion than I could do in class because I tend to run out of time. So I'll try to take the time to properly go over it in a recorded video and in a flipped classroom setting so that you get the opportunity to, go through it at your convenient time and then get back to me with questions. Okay, so let's get started. This is the part one of MOSFET lecture. So as you can tell, there will be other parts. We'll start, and I will start with a disclaimer. This particular lecture will be heavy with band diagrams. And I told you several times before that band diagrams are kind of like the language that semiconductor folks use universally. There is no getting away from them, but I totally understand that they can become boring and a little bit confusing. But trust me, if you pay attention and try to understand it and ask me questions, hopefully it will feel much easier to grasp than it actually might be otherwise. So in the first slide, I have a few comments. These are all taken from textbook. You can read them and you'll understand why these are important. But in simple word, look at the first sentence. The basic transistor action is the control of current at one terminal by the voltage applied across the other two terminals. This is an interesting comment. I feel like, think of a BJT, bipolar junction transistor, which is NPN. You can apply an input in one of the terminals and deal with the other two terminals. Say maybe A is the input and B and C could be the output terminal. That's the signature of a transistor. You are controlling the flow of current between two terminals using a third terminal. Does it make sense? That's what people were after. Engineers, when they started looking for transistor structures, they were trying to make exactly that. There has to be a control terminal that influences the flow between other two terminals. That's how you make a transistor. So this is a very simplistic approach. As you see, BJT has three terminals. MOSFET is a similar device, and I'm going to oversimplify it now. NPN, you still have a NPN structure. Interesting. So there is a BJT structure within MOSFET structure, except for the fact that you have an additional gate. This is a gate layer, and you apply voltage to this gate to control current between the other two terminals, A and B. Isn't that similar to BJT? It is similar. That's why it's also a transistor. MOSFET, it ends with T. T stands for transistor. So it's essentially a transistor still, but it works with a very different principle of operation. And the structure is also different. And I will tell you why this gate is necessary and why do we introduce it in the structure, okay? But I'm just getting ahead of myself and letting you know that these are actually similar. They are both transistors. They allow you to control the current using a third control terminal. One more thing, MOSFETs and BJTs, they are both of two kinds. So for NPN and PNP BJT, you have NMOS and PMOS. So basically similar to what BJTs are. I mean, if I ask you how many BJTs types can you make, I mean, logically you can come up with two structures, NPN and PNP. Similarly, logically you can come up with two structures for MOSFET, and they basically stem for NPN and PNP, and then on top of it you have gate and gate. So see, there are a lot of similarities between BJTs and MOSFETs. Given that there are two types of BJTs, there will be two types of MOSFETs. Okay, and these MOSFETs are complementary in nature, and you'll see how they're complementary. Whatever you talk about, I mean, whatever applies to one of them, the inverse will apply to the other, which is interesting because that makes it easy for us to explain. We could just explain one, and the other one will be similar. The best part is by combining these two complementary kinds, you can come up with interesting circuit, and that's why we often use the term CMOS, right? CMOS sensors, CMOS circuits, CMOS technology. So CMOS stands for complementary MOSFET. C stands for complementary, okay? So apparently the fact that you have two types of MOSFETs that are complementary, any electronics that you do with this is CMOS electronics. We can take it for as for granted, like, okay, what's the big deal? I mean, we have been doing CMOS for a while. No, interestingly, a few decades ago, complementary MOSFET was not possible. We could only make one type of device. The other type was still difficult to make. For example, the PMOS specifically was way too bad. You could make NMOS, but you couldn't make equally good PMOS. So you had to struggle a lot. Technology had progressed, and now we are able to do both. Okay, but every once in a while we fall into the same type of loophole. For example, right now we are working on high temperature electronics, which is a part of extreme electronics. High temperature electronics is necessary for applications like hypersonics. For example, when something moves extremely fast, things get really, really hot, and conventional electronics will just melt away, right? You have to come up with unique devices. We are struggling with exactly the same problem. We don't have complementary. We have one kind of device. The other type, complementary, is difficult to make. So basically back to square one again. So the technology folks are trying to make the other kind of device right now. So CMOS electronics was at that stage a few decades ago. Now we're good. We do complementary MOSFET. Okay, now let's start with the simplest slide in today's lecture. This is the simplest possible slide. We will not even get to the FET structure in this lecture. We'll just talk about, one second. We'll just talk about the MOS, MOS. See, there is MOSFET, metal oxide semiconductor field effect transistor. We'll not even get to the field effect transistor part in this lecture. We'll just discuss MOS, metal oxide semiconductor. In fact, MOS itself is a device. MOS, often in different textbooks, they call it MOSCAP or MOS capacitor, metal oxide semiconductor capacitor. It is a type of capacitor that could be dynamically tuned. Remember, in one of the previous classes, I took some time to highlight how dynamic tuning is a big deal. In a diode, you could dynamically tune capacitance, so it was great. So similar to that, MOSFET is a more complicated device than diode, but that also provides you a dynamically tunable capacitance. So even if you don't use it as a FET, you could use it as a capacitor. Okay. All right, let's start. Please pay attention because I'll be drawing a lot of things, and all of these are taken from textbook. And my intention is to compress 2-3 pages of textbook in one slide or 2 slides. Okay. So if you pay attention, you don't have to worry about it anymore, I hope. But if not, then again, I know how that goes. Basically, you'll be super confused, and none of the other lectures will make any sense because they are correlated. Okay, so this is the basic structure. You start with metal. You have an insulator, and when I say insulator, typically we use oxides as an insulator. There are different kinds of insulators. For example, wood is an insulator, glass is an insulator. Interestingly, glass is nothing but an oxide. So similarly, most oxides are insulators. So for the most part, any device when you see that there is an insulator in it, we typically use oxide as an insulator. You might be wondering why oxide. Oxides are easier to fabricate, and for the longest time in chip making industry, people used silicon dioxide as the insulator. Interesting side note, one of our professors told us this interesting story. He told us that the reason why CMOS or silicon was so successful, I mean, people started making chips with germanium first, by the way, and then they moved away from germanium, moved to silicon. And now, California has a Silicon Valley, not a germanium valley, for example, right? Why was silicon so successful? Well, people will tell you different things, but one of the things, which I also agree with, by the way, is it's so easy to make silicon dioxide. So you take silicon, you warm it up, it reacts with oxygen in the air, and it creates a really nice thin layer of silicon dioxide. So that oxide is like a magic oxide. That's what he told us, and I later checked out, and that's really the case. Silicon oxide is like a magic oxide. It creates really nice uniform bond with the layers underneath. So you have a layer. Semiconductor is basically just silicon. On top of it, you have silicon oxide. How do you make that oxide? You just warm up the bottom layer, it reacts with the air on top of it, and creates a really nice thin layer of silicon oxide. Super easy, super cheap, repeatable process, and reliable process. That's why it was easy for us to make MOS structure, metal oxide semiconductor, because you get these two for almost free, and the other one is what you have to deal with. Basically, how do you deposit a metal layer on top of an oxide so that it doesn't just, etch away? Still with me? Okay. So this is the metal oxide semiconductor structure. Super simple if you think about it this way, that you can use this structure to separate out two types of charges, positive and negative charges, because there is an oxide in between. Oxide is an insulator. So as if you have two layers of charges separated by an insulator, obviously, as you can see, this is nothing but a capacitor. Okay, so this could be treated like a capacitor. And let's get to the second part of the slide here and see how that capacitance comes into the play. Imagine you apply a negative voltage to the gate terminal. And negative voltage brings in electrons. And let's consider, without any loss of generality, that the semiconductor that you had here was p-type. Let me just zoom in here a little bit. Okay, it was p-type semiconductor. Please tell me, will a p-type semiconductor have an abundance of electron or abundance of hole? Holes. Holes are positively charged particle. When you apply negative voltage here, these electrons will not be able to directly go inside the semiconductor because there is an oxide stopping them. Oxide is an insulator which stops them, right? But they should still be able to attract these holes, which are positive charges. So the holes will pile up closer to the surface. So, they will pile up along the oxide. And that's what you see here. There is a accumulation of positively charged holes closer to the surface when you apply a negative voltage to the gate. Okay, that means, and as you see, you have as many positive charges as there are negative charges. So this is nothing but a parallel plate capacitor. You create a parallel plate capacitor in a MOS structure. The more voltage you apply, more charges will accumulate. And this process, actually, it is called accumulation. So MOSFET has different modes of operation. Okay, accumulation, depletion, inversion. You could always divide it up into strong inversion, weak inversion, but that comes later. We'll discuss this in the next part of the MOSFET lecture. But accumulation is a mode of operation for MOSFET. When you apply a voltage that invites the opposite kind of charge and accumulates them closer to the surface. Remember, this is not the interesting mode. This is not the mode that we use for digital electronics. Still okay? So that's why we started with it, because we'll be done. But then the next mode is the one that we practically use to make circuits and logic and processors out of. Okay, let's talk about it. What if you apply a positive voltage to the gate? So this is a voltage, representing a voltage that's being applied. You apply a positive voltage, and you had p-type material, so it had positively charged holes. These holes will be repelled by this positive voltage, so they will move away from the surface. Are you guys still okay? Now, if that is the case, what remains here? In this zone, you basically have almost no holes left. Okay. There is a term that we always use when we try to represent that a region in a semiconductor is devoid of electrons or holes. The term is called depletion region. Right? Remember in the diode lecture we talked about it. So you essentially create a depletion region. You know, in a diode, when you connect N and P, there you go. You have a depletion region which is permanent. You cannot get rid of it ever. But in a MOSFET, you create the depletion region by applying a voltage. If you remove that voltage, the depletion region is gone. You see that there are similarities, but there are also differences. That's why this is more complicated device and more useful than a diode, right? So pay attention and ask question. So this is a depletion region that you create by applying a voltage. What was the other name for depletion region? Anybody remembers that? Thank you. Yes. So that's what you see here. This is a space charge region, but it has been induced. That's why it's called induced space charge region. So you can induce it, you can completely, erase it out by removing the voltage. Okay. And I'm familiarizing you with the terminologies that the textbook use, right? And also the semiconductor folks use. So there is an induced space charge region within the MOSFET structure. That was the simplest slide for today's lecture. Move on. And I told you even before we started, there will be a lot of band diagrams. Pay attention. Hopefully things will be easier. Let's do it. So let's start with the band diagram of a MOSFET structure. See, I like to draw this figure when I explain MOSFET. A MOSFET, essentially, the MOSFET structure looks like this. So you have N-type semiconductor, N-type semiconductor, P-type semiconductor here. And then on top of it, I think I should probably just give you this high-level conceptual description first, so that you don't feel completely lost, right? You can somehow relate to where we're going. So please pay attention, it's not there in the textbook. Okay. All right. So this is your gate. There is an oxide. There is an oxide. And the gate is nothing but a metal. All right. Now, since this is P-type, notice that you have a PN junction here and another PN junction here. So it's like back-to-back PN junctions, don't you think? So if you have back-to-back PN junctions, based on your understanding in the lab, a PN junction would only let current flow in one direction and restrict the other direction, right? But the other PN junction will do the opposite. So apparently when you have back-to-back PN junction, it will not allow current flow, practically, don't you think? So this terminal and the other terminal, let me use different color here. This could be source and drain. They're called source and drain, and one of the terminal that controls it is called the gate. So between source and drain, you cannot really flow any electrons because there is a back-to-back diode structure sitting in there. Are you guys still with me? Okay. Try to visualize it in a way that when an electron is trying to go from N to P, there is a diode, means there is a built-in potential. So the electron, when it tries to go from N towards the other N, it will see a built-in potential. So it will not go, it will stop. Okay, now, what happens when I apply a positive voltage to the gate? So I have applied a positive voltage. P-type material is full of positively charged holes. But when I apply a positive voltage, that positive voltage will repel the holes away. And where will they go? They will dive deeper into the P-type material. Don't you think? So then what? Then closer to the surface, you create a region where there is no holes left. Are you guys still with me? Please pay attention, because after I tell you this, you will not be able to read it anywhere else. Okay, so I'm using a different approach towards explaining it. All right. So by applying a positive voltage, you repel away the holes and you create a zone for you to make something else later on. It's as if like you're clearing away path for the electrons. You want the electrons to flow from source to drain. That's what you want. But there were no way, because there were back-to-back diodes sitting in there. You want that back-to-back diode to move over and create a path for the electrons to flow. First thing that you do is you remove the holes so that there is an empty path. There is not yet a really nice path, but there is an empty path. At least it's not restricting. Now, what happens when the majority carrier holes move away? I told you that in any type of semiconductor, there is always two types of carriers, electrons and holes. In p-type, there are more holes, they're majority carriers, but there are also electrons. When the holes move away, the electrons realize, hey, that's what we like. I mean, see, look at that. There is positive voltage. Let's go there. So the minority carrier electrons can, I will use a different color yet again. Minority carrier electrons from the p-type material will go all the way and they will try to pile up in this region. Still with me? Still with me? Why? Because the holes moved away. It's a safe place for the electrons now to accumulate, because there is a positive charge being applied to the gate, which they like. So the electrons will gradually come and create a layer, really thin layer. This layer, I'll tell you the name later in a second. But imagine when you have a layer of electron, don't you think that closer to the surface, it feels like this is an n-type material? Because there is a lot of electron concentrated in a certain semiconductor zone. It looks like an n-type material, don't you think? Still with me? And this process is called inversion. Why? Because you have literally taken a p-type material, applied a voltage, and converted a zone within the p-type material into an n-type material. That's called inversion. Okay? So you have inverted this zone into n-type. Now, can I draw it this way, that this is n-type, this is also kind of temporarily n-type, and then there is another n-type material here. Now, don't you see that there is a really nice clear path for electrons to move from one place to the other? Still with me? So you have created a really thin channel closer to the surface of the oxide for the electrons to flow from source to drain. I'll tell you why they will flow from source to drain. They will not just say, huh, let's check out the drain. No. By the way, you have to also apply a voltage. Electrons don't move around unless you provide some sort of encouragement, external voltage or temperature difference, right? So if you apply a positive voltage here and negative voltage here, only then, I know it's getting really, really busy and messy. That's what I told you. Like, you have to watch when I draw, but because after that it will be messy. Now, if I erase everything, it's gone, right? But my point is, this electron will go all the way from left to right. I know it's messy, so I'm going to get rid of it. I'm going to draw it one more time. N-type, N-type, source, drain. One more time, okay? So this is metal, oxide. Let me just make it as if it's an insulator. And then when you apply a positive voltage to the gate, the holes move away deeper into the substrate. So you create a layer of pseudo n-type material. This is really, really thin, by the way, really thin layer. Okay? It's called inversion layer. And now, if you apply a voltage, positive voltage in this terminal and negative voltage on the other terminal, in this n-type material has lots of electrons, don't you think? The other one will also have electrons because this is also n-type material. But since this is positive, electrons from source will tend to travel through the channel all the way to drain out of this device. So there will be a flow of electron. How can you stop the flow of electron? Tell me. Super simple. Can you tell me how do you stop the flow of electron? Thank you. Yes. The moment you remove this voltage, the holes will come back. This channel will be disrupted. You again have back-to-back diode, so it will choke the current. Done. Isn't that a super simple structure? You apply positive voltage, create a channel, then electrons can flow. You turn on the device. You remove the voltage, the device turns off. So whatever happens to the gate, I could just symbolically represent it in this way. This is a gate. If the gate has a positive voltage, it allows current flow from drain to source. If there is no positive voltage, it doesn't allow current flow. Super simple. So you have a switch. If it is on, current flows. If it is off, current doesn't flow. As simple as that. So that's where we are headed. Even this is simplistic, by the way. Okay, but that's where we are headed. Very simple concept. And by the way, this concept, I can tell you a backstory. In 1925, someone who actually proposed the structure of MOSFET, right? Super. I mean, just imagine the impact. Everything in our digital universe is made out of MOSFET now. But that was 1925. He drew something on a piece of napkin, like at a restaurant. He was speaking with his friend, like, hey, I have an idea, blah, blah, blah. How about this? So they had nothing else to work on. So they just took a napkin and drew on top of it. And I mean, yeah, looks like an interesting idea, but how do you make it? It cannot be made. How do you control it? No, it's okay. Nice, funny idea. So he took a patent, by the way. He took a patent, he got the patent, but I don't know if you know this, patents are only valid for 20 years. Okay, so so you get a patent, you're given exclusive right to work on that for 20 years, and then others can take over and the patent could be open. We had a patent, obviously 1925, doesn't matter. 1945, people couldn't make MOSFET. So nothing happened there. But the same concept that I just explained to you, this was his concept. And this is the concept to this day that we use to make MOSFET. And people realize they start in 1958, when they started making ICs, they couldn't make MOSFET. Even then, that was impossible. Only a few decades ago, we were able to actually make MOSFET. So now we make MOSFETs. Everything is MOSFET. So it took more than 50, 60, 70 years for that idea to come into fruition. You know, ideas could, I mean, it may not make sense at this point. You might have a crazy idea. It may not make sense at this point. Maybe you will not even be there to see your idea come to fruition, but you never know. Any idea could possibly become legit at some point. Similar story, around 1960s, somebody came up with an idea. Have you thought about how we store information in our computers and cell phones and flash drives? We always save everything in binary format, right? Digital format. Why do we deal with binary? Because binary has two states, 1 and 0. It's easy for us to represent two states with a switch, like a MOSFET. MOSFET can be on or off, like you just saw. It could be on or off. So we could use a MOSFET to represent 1 or 0. So that's why we deal with binary, because that's the only number system that requires only 2 digits. Okay, now getting back, this is processing is one thing, but how do you store that information? MOSFET cannot store information. Okay, MOSFET processes information, and then the moment you remove the voltage, it's all gone. Right? You start from 0 again. So you have to have specialized devices and electronic systems to store information. That file that you just saved, that photo that you just uploaded, that photo that you just took, they're all being saved in physical form, in something, right? So that one selfie that you took, that would be converted into millions of bits of information, ones and zeros. If you have 1 million bit for 1 megapixel, there will be 1 million devices like this guy, this simple MOSFET, okay, saving them. And let me get ahead of myself. The most common memory device that we use is called an SRAM. An SRAM has a minimum of 6 MOSFETs. So you need at least 6 MOSFETs to store 1 bit of information. Just imagine that. Okay, that's called SRAM, static random access memory. I don't want to take too much of a tangent. There is a reason why I'm telling you this. Okay, so please bear with me for a second. Are you guys still with me? Okay. My point is, to store 1 bit of information, you need that many transistors, which is insane. But this device, this circuit per se, has been with us for more than about 50 years now, right? So people have been using this same idea, same concept to store information. But back in 1960, somebody gave a different idea. Hey, let's take a material. You know about crystal, right? Amorphous, crystalline. You know that. We've started with that, right? Amorphous, crystalline. Which type of material do we care about the most in semiconductor industry? Single crystal. because they're easy to describe mathematically and predict, right? Amorphous is all over the place. How do you mathematically describe them, right? So they, the scientist, he proposed that, hey, maybe there was a type of material called GST. I'm not going to get into the detail of it. Let's take GST. Let's use current pulses to melt the material. And it turns out when you melt the material and let it cool down, it becomes amorphous. But if you melt it really, let me just rephrase that again. If you melt it fast and cool it fast, it becomes amorphous. But if you melt it slowly and let it cool down slowly, it becomes crystalline. Am I making sense? So the atoms get time to organize and become single crystal again. But if you do it really fast, it becomes amorphous because they stop wherever they were. So when it is amorphous, it has a very high resistance. When it is crystalline, it provides low resistance. And we need two physical states to represent 1 and 0. And his proposal was, let's use high resistance state to represent 0, low resistance state to represent 1. So thereby, by using chunks of material, small material, cubes, you could represent different logic, different memory. That was his idea back in 1960s, say. The problem is you have to literally melt a material, and they calculated, and it was insane. Like, how about like to save one bit of information, you need to melt something and then let it cool again. The amount of energy required was insane. So everybody laughed, like, okay, come on, man. Like, anyways, so yeah, fine. 20 years ago, this idea was revived. You know why? Because now we are basically using it. We are using it. Industry is using it. It's called phase change memory. So one of the emerging type of memory that is up and coming. Why nothing changed in the idea? Exactly the same idea. Nothing changed. Can anybody tell me what changed within these few years that now it's all on a sudden it makes sense, but at the time it didn't? Anyone wants to try? Nanotechnology. Okay, I'll tell you what. Apparently, the amount of energy required to melt something is related to its volume. Okay, at the time in 1960s, we could only make big electronics, not even micro level, even more than that, bigger than that, right? So for that size of a material, it used to take a lot of energy to melt things down. But over the years, we managed to make things smaller and smaller and smaller. Now we can make nanoscale material, same material at a nanoscale. So when you're reducing length, width, and thickness, you're basically having triple effect. You are reducing the volume essentially. So there is a cubic dependence. So the energy required to melt the material is all on a sudden extremely low. So now you can do it with simple nanoampere level current. As simple as that. So now we use the exact same technology for memory storage, right? That tells you something. I didn't want to just let you go with 1925 story. Like, this could be an outlier. Okay, somebody had a great idea that didn't fly. Okay, people didn't care, but now we all care. We all care about that idea. Okay, so similarly, these type of stories are found everywhere, like more often than you can think. Right? Anyways, that's the sad truth. Oftentimes, many ideas that people will laugh at will probably change the world. All right. So now that you see a high-level vision about how MOSFET works, what are we trying to achieve with it? Let me get back to this slide, which is super boring in my opinion and doesn't look as interesting. But I'll tell you why we still have to go through it. I haven't erased it. That's a good thing. Please notice, I'm going to draw something on top of it, okay? On top of this super messy. So this is a MOSFET structure. I'm going to draw it now, okay? Are you looking at it? Here, just take a look at this region. Just this region. So MOSFET has two interesting directions. This one, maybe y dash. And then the other interesting direction is along this line, x dash. For this lecture, we'll mostly be dealing with this vertical direction, y dash. Okay? That completely obliterates this source and drain. So there is no concept of source and drain today. Even I'm getting scared of this mess now. So let me just metal oxide. What I was trying to tell you was we are gonna only focus on this region, which is y dash cross section, say. But at some point in our lectures, we'll talk about this x dash as well. Yes, all with me so far? Can anybody guess x dash will be easier for you to understand if you understand BJT? Why? Can anybody tell me why? Can anybody tell me why? What was here? N, P. Just take a look at this cross section. What are you going through? N, P, N. Right? Does that make sense? Don't you see? N, and then there is P, and then there is N. So basically, you are going to look at a BJT essentially when you go through XX dash. So we'll do it later because I assume that by that time you will hopefully have better idea about BJT. But this is new. YY dash is new. We haven't seen anything like that before. Do you see why I had the heterojunction lecture right before this? What did we learn there? Metal semiconductor heterojunction. What are you looking at here? This is a heterojunction. You have metal, you have oxide, you have semiconductor. Different kinds of materials merged together. So this is a heterojunction. Okay. All right. So let's get back to this. That's why you're looking at this diagram where you have a second. Yeah. Where you have the gate, you have the oxide, and then this is the semiconductor. Okay. It's flipped so that it's easy to draw. It's flipped. Instead of vertical, we are just flipping it horizontal, 90 degrees. All right. Now, folks, oxides are not really that interesting. They don't really do much except for restricting electrons to go from gate to the other side. So as you see in all of these figures, it's nothing, just a chunk of rectangle, done. So ignore it. Semiconductor. You see, wherever there is semiconductor, there are multiple levels: conduction band, valence band. You know all of them. What is this blue one? Intrinsic Fermi level. What does that represent? Literally the midpoint between conduction and valence band. Simple. So none of these are new to you, are they? What is the other one? Fermi level. Why is the Fermi level close to the valence band? Because this is p-type. You know all of this. So no need to worry about anything. So you understand, I hope, this section. This is basically representing a semiconductor band diagram, which is a p-type material. Can I not do it for n-type? Can you do it for n-type? Just take the Fermi level, put it close to conduction band. There you go. So you have the other type of MOSFET. That's what I'm telling you. We'll always deal with one type, and I'm going to quickly tell you, you can do the same for the other. All right. Now, gate is simple, super simple to deal with. Why? As we discussed in the heterojunction lecture, metal just has a Fermi level. Done. No conduction band, no valence band, no blah, blah, blah. So this is just treated like there is a Fermi level. Done. So we are not going to do much with the gate or the oxide. We'll do everything with the semiconductor and see how the semiconductor is affected by what happens at the gate terminal. Okay, let's do it. So this is an idealistic picture where all the bands are flat. Let's consider what happens when you apply a negative voltage to the gate, a negative voltage to the gate. And I already explained that using this diagram. So correlate this with the next diagram. Let's do that, please. So negative voltage. What happened when you apply to negative voltage to the gate? Tell me verbally. What happens to the p-type semiconductor? P-type semiconductor had holes which are positive charge. They will accumulate closer to the oxide, don't you think? Because they like the negative voltage. So how do you represent hole accumulation? Where are the holes? Are the holes in the conduction band or in the valence band, folks? Tell me. They're in the valence band, okay? So now if I mean, just to represent that the holes are more prone towards going closer to the oxide now that you have applied a negative voltage. Let me show you something. If I draw this band diagram in this way, like it is bending this way, would it be easier for the holes to get to the oxide or difficult to get to the oxide? What do you think? Difficult. Are you still with me? So notice that the bands are bending this way, basically. That means the holes can easily go. I think I use this analogy. Holes don't exist, you know that, right? They're basically like opposite of electrons, not having electrons. So wherever the electrons go, holes will go in the other direction. typically electrons wants to go down in energy. So holes will want to go up in energy, opposite. Remember that, okay? So they're like balloons. This is another analogy, like helium balloons. If you let some helium balloons go, they will also try to go as much up as they can do. So these holes will try to accumulate and they will try to go up. That's why it is easy for them if the bands bend this way. So that's what the bands represent. It's bending the other way, okay? It will make more sense when I get to this diagram, because then now you'll be dealing with electrons. So imagine you apply a positive voltage. All right. But one more thing, whenever the band bends here, conduction band will also bend in the same direction. Who can tell me why? Why? Thank you. Thank you. I appreciate that. Yes, you have to maintain the same band gap, of course. So if this guy bends this way, the other one will also have to bend the other way, the same way, because otherwise the band gap will change, right? So there you go. If you could figure out the bending for one of the band, doesn't matter which one, conduction, valence, you could do the same for others, okay? All right. Now, let's see here. Folks, pay attention, the band gap. I just want to also explain one more thing. How many of you remember this concept that we talked about? Material A, material B, conduction, valence, conduction, valence. Imagine you have a Fermi level here. You have another Fermi level here. Fermi level, Fermi level. Is it material A p-type or n-type? Quickly. P. Is material B n-type or p-type? Both of them are p-type because Fermi level is closer to valence band. Which one is more p-type? A. So you remember that if the Fermi level moves closer to the valence band, it becomes more and more p-type. Now let's get back here. This is important. I wouldn't have told you this otherwise. So this was p-type to begin with. This was p-type to begin with, as you see. Closer to the surface, notice that the band bends in a way that the Fermi level is even more closer. So closer to the surface, it has become even more p-type than it previously was. Isn't that the right thing? Because the holes are accumulating closer to the surface. So the surface is becoming more and more aggressively p-type than it was before. Does that make sense to you? I'll tell you why I just chose to highlight this. Because the opposite will happen. You don't care. It was p-type. It is even better p-type now. Okay, who cares? Nobody. But what happens? It was p-type, but all of a sudden it's no longer p-type. It's n-type. What is that process called? Inversion. Didn't I just show you that that's how the MOSFET turns on, by inversion, right? So that's where things will get interesting, and we'll talk about it here. Let's do it. Okay, positive charge. So you apply positive charge here. When you apply positive charge, you basically make it difficult for the holes to come closer to the surface. You have to repel them out, right? So that's what you do here. You bend it in a way that the holes cannot really come closer, so they have to move away. Or you could think of it in terms of electrons. You are inviting the electrons to come. Where are the electrons? They're not here. The electrons are in the conduction band. Now, free electrons, actually. The free electrons are in the conduction band. Electrons are everywhere, but free electrons are in the conduction band. So the free electrons will like to come closer to the surface if there is a bending this way, because electrons want to minimize their energy, don't you think? So the electrons will be encouraged to come closer to the surface, to the oxide. Still with me? So if you tell me something, if I apply one positive voltage, maybe this is the bending. If I apply even heavier positive voltage, what happens then? What happens then? Curves more, exactly. So it will curve like this. I should have used a different color, maybe. Let's consider that it's more positive voltage, so it will bend heavier, like this. So electrons will be happier to come closer to the surface. Still with me? Okay, it's not really that interesting here. Sure, we understand that, but let's come here and we talk about inversion layer now. Ready? And that's exactly what I just told you. I drew on top of this guy. Like what if you have a more stronger positive voltage, right? Now look at this figure. That shows you exactly that. When you have a more or large positive voltage, it bends so much that something happens, and I'll show you what happens. Ready? Let's see. Look at this section. Is the material N-type or P-type? Is the Fermi level closer to the valence band or conduction band? Tell me. In this zone, valence band. So this should be P-type. It was P-type to begin with, of course. What do you expect? It's P-type. It is still P-type. But closer to the surface, notice, this is your Fermi level. Fermi level didn't change, by the way. It's a flat level. But this band's bent in a way that the conduction band is now closer to the Fermi level than the valence band. You see that? It bends so much that now you have brought the conduction band closer to the surface. So essentially, what you have here is inversion. And I basically explained it using the other cartoon, right, before. You repel away the holes, electrons pile up closer to the surface, and they make it essentially effectively N-type. And that's what you see here. So in a MOSFET, all action typically will occur closer to the interface between oxide and gate. So see, oxide, I mean, this guy has nothing to do. But without this guy, this effect will not occur, as you see. So oxide is apparently like meaningless thing, you might think, but this is basically creating all of these interesting features. All right, so that's called inversion layer of electrons. And, one more thing to point out. Still with me? Okay. Before letting the electrons pile up here, we had to move the holes out, don't you think? So when I moved the holes out, what did I call that layer that was devoid of free holes? I called it depletion layer because I depleted the material of free holes. Does that make sense? So this layer, this zone is called the depletion layer. And now get used to this, make this a habit. Wherever you see a bending in bands, you understand that there will be some sort of depletion layer. Some kind of charge will have to move away to make way for the other kind of charge, right? So electrons are encouraged to come here. That means hole must have been kicked out. So this is a type of depletion layer that you have also seen in diodes. So this XD, D stands for depletion layer. Okay, you don't understand why there is a T here. I'll explain that towards the end of this lecture. I don't know whether this will be today, but this lecture. Okay, so remember the XD, the T has an extra meaning. T stands for threshold. Why are you so sad? Trust me, I know how boring these things can get. Okay, so I'm with you on that, but I still have to do it. I mean, I'm given the charge to teach this stuff. It is really difficult. Okay, so as part of a National Science Foundation project, we are teaching chip design to high school kids, class 9. Now imagine how difficult it could be to teach this kind of stuff. So in the last class, we taught them MOSFET. Obviously, we are not going through all these contents, right? We don't show them math. We don't show them band diagram. There is no band diagram. I use the cartoonish description to explain what goes on. Maybe some animation, right? As easy as you can make it. But honestly, you are at a stage of your career where you have to get into action. So you have to get your hands dirty to some degree. But this is not the deepest understanding, by the way. The deeper, for example, if you join Intel, there will be a 6 months to 1 year long training session. Basically, you will be a trainee for a while, and they will have internal training, and you'll be attending classes. Okay, and there will not be classes like this. There will not be homeworks and exams like this, by the way. But they will assume after the course you understand everything. So if you don't, you have to ask your other friend, not even that much of a friend, maybe. Here, you guys are possibly real friend, but there, your colleagues who might end up being a friend at some point, but you're not friend yet, right? So you'll be hesitant to ask, hey, I didn't really get it. Yeah, I got it. It's easy. But you actually didn't get it. Okay. So I know, because it's a little bit tricky. When I was an intern, I actually went through the same training, because I mean they have training for everybody, intern to senior to junior, the same training, everybody sits together. So I know how that works, and whoever was like taking the class assume that, oh, this is understandable to everybody, because they are working on this for 25 years. What do you expect, right? This is like bread and butter for them. Anyways, moving away. But if there are questions, ask me. Don't give up. Please don't give up. Okay, you don't. And these are not that difficult, honestly, if you pay attention. Okay, move to the next one. This will be a repeat of what we just discussed. But can you tell the difference? Instead of having a p-type semiconductor here, we will be having n-type semiconductor. So whatever we have just discussed, the same thing applies here. Okay, exactly the opposite. So whenever you have a positive voltage, you have accumulation of, let me explain that very quickly. At least for the first one, I should do that. But the next one, when it comes to repeating the same, I will just say, okay, same. Okay, read it at home. So imagine if you apply a positive voltage to the gate, and this is now n-type semiconductor. How do you know? Fermi level closer to conduction band. You can read them now. Okay. So when you apply positive voltage, electrons will be encouraged to pile up closer to the surface. How can you encourage the electrons to come closer to the surface? By bending the bands this way so that the energy is lower. That way the electrons will like to come closer to the surface. So simple. And this is called accumulation. Why don't we call it inversion? Because you are basically, you had electrons, you are bringing electrons. You are not inverting anything. You are just accumulating more and more electrons. That's what the name suggests. Imagine if it were electrons, but now you're piling up holes. That is inversion. Okay, that's what you do here by applying negative voltage. Imagine if you apply negative voltage here, electrons will be moving away from the surface. To represent that, we show it in a way that the bands are bending upwards. That means it's becoming difficult for the electrons to come closer to the surface. So they're moving away. That also means holes will like it. The holes are like helium balloons. So they will like to pile up here in these zones. And the more negative voltage you apply, the more bending you get. And at some point, the bending will be as such that here, inside the body, it is n-type because the Fermi level was closer to the conduction band. But at the surface, the bands bend so much that the Fermi level is now closer to the valence band. So it's essentially p-type closer to the surface, interface of oxide. So that's the inversion again. So it's an inversion layer of holes. So exactly the opposite concept, okay? This is elegant, I think. This is nice because if you understand one really nicely, the other one will just fall in place. Okay. Now, more band diagrams. All right. It's okay. It's the same thing that we just discussed together. But now we have some more terminologies to take care of. There is no getting away from it. We'll be using the terms like surface potential, metal semiconductor work function difference, flat band voltage, threshold voltage. These are standard terms. So you need to educate yourself about this term. And there is simply no way to explain them without showing band diagram. Okay, so let's pay attention. Let's do it. So we are looking at the energy band diagram in the p-type semiconductor, and we are going to learn about surface potential. I didn't even have to tell you that this is p-type because you see Fermi level closer to the valence band. Okay, that's p-type. So we already discussed it. All right. So can anybody tell me? I'll not show you the stuffs on the left. Just looking at this band diagram, can you tell me whether we have applied a positive voltage to the gate or a negative voltage to the gate? Go ahead. How do you know? Okay, thank you. Yes. So when you apply positive voltage, you encourage the electrons to come closer to the surface, and obviously electrons need to slide down. So obviously you must have done that. All right. So sure, you see, they haven't even showed what type of voltage they apply because you should know this by now. Okay. Now, notice there is a bending. There is an amount of band bending that you have achieved. And that bending is the same for conduction band, valence band. And I told you, intrinsic Fermi level is basically nothing but a shadow of conduction and valence band. It's shadowing everything else and staying midway between the band, right? So don't you think this bending will also be the same geometrically if the distance is all the same? So the amount of bending, we somehow have to find a way to measure the amount of bending. How much bending did you get? that measurement of the bending is called surface potential. Okay, and we like to make it sounds fancy, so we use chi instead of something else, and S for surface. So oftentimes you use chi S. In some textbooks they use phi S. They will never use AS, BS, CS because this is not as fancy. They'll always use alpha, beta, zeta, eta, those kind of stuff. Difficult to type, but it is what it is. It looks nice. For this particular textbook, they have used phi S, surface potential. Okay. All right. Super simple. Like, how much bending did you get? That's phi S. And now, why is it called surface potential? There is a reason. The reason will probably not be super clear in this slide, but when we discuss flat band voltage, it will probably be clearer. But I'm still going to tell you quickly. When you apply external voltage to the MOSFET structure, say you apply 1 volt, the entirety of the voltage will not show up at, so this is oxide, by the way, this was oxide. This is semiconductor. So this is the surface between oxide and semiconductor, don't you think? This is the surface where the actual semiconductor begins. But remember, if you apply 1 volt, that complete 1 volt will not show up at the semiconductor interface. A portion of that voltage will drop across the oxide, which is essentially loss, because oxide is not doing anything. Does that make sense? We still need it, because otherwise none of this will occur, but you lose a portion of your applied voltage at the oxide. So when you apply voltage, a portion is dropped across the oxide. So you get the remainder at the surface. So this potential that you are getting, this is surface potential, the potential or voltage that actually appears at the surface. Does that make sense? Now, if I tell you that this is 1 electron volt, and I'm going to use this electron volt for now. How much voltage have you applied? Have you applied 1 volt? No, you have applied more than 1 volt, because a portion dropped across oxide and you only got 1 across the surface. Remember that. Does that make any sense at all, folks? No? Just to clarify again, you have metal, you have oxide, you have semiconductor, and all the action occurs inside the semiconductor. Electron flowing, holes flowing, generation, recombination, whatever, you name it. Everything occurs within the semiconductor. Oxide is just doing nothing. Okay, a metal is just being used to apply positive or negative voltages. That's all. Okay, so action occurs in the semiconductor. So you care about the voltage that appears at the surface, this surface of the semiconductor. That's surface potential, phi S. Now, if you apply a voltage VG, say gate voltage, externally, a portion of VG will basically drop across the oxide, Vox. And the other portion will go and work with the semiconductor. That's phi S. So VG is actually equal to the sum of these two, where Vox is nothing but a loss, and phi S is basically leading to all the action. That's surface potential. Does that make sense? So just by looking at the bending, can I say how much voltage was applied? No. You applied more voltage than how much bending you are getting, because a portion of it was dropped across the oxide. Does that make any sense to you guys? Okay, all right. Otherwise, I could have, remember in the diode lecture, just by looking at the difference between Fermi levels, you could tell how much voltage was applied, right? Okay, 1 volt difference, so I applied 1 volt. The difference between the Fermi level. But here, just by looking at the bending, you cannot say how much voltage is applied, because there is an oxide sitting in there which will take a share of the voltage. Are you guys still with me? Now, one more thing to clarify. Don't take this as the final equation. There is one more loss term that I haven't showed you here because we haven't discussed it. I told you flat band, right? So when we discuss the concept of flat band, there will be an extra term called V flat band, and that will also be a loss term. So keep that in mind. I'm just making it simple, at least for this stage. Okay. Now, if I show you this band diagram, can you tell me the surface potential? Yeah, just by looking at the bending and calculating how much bending you got, that's your surface potential. Okay. And there are ways to calculate that. Let me show it here. How many of you recognize this equation? We dealt with it in the entire p-type semiconductor lecture. This is basically the difference between intrinsic Fermi level and Fermi level. If you don't remember, just go back to the very simple NPN semiconductor lecture and see this equation. Vt is nothing but kT over E. So that's how it was written. Vt is thermal voltage, kT over E. Essentially, this is still a semiconductor. So all the equations that you've learned so far about semiconductors all apply here. Nothing changed, okay? So phi fp is basically the difference between the Fermi level and the intrinsic Fermi level. For MOSFET, people tend to use this term more than the other devices. This is a more useful term or variable than the other devices, okay? Just keep that in mind. What is phi fp? The difference between Fermi level, intrinsic Fermi level. You might be wondering why P? Because this is a p-type semiconductor. If it were n-type semiconductor, we would have used what? Phi Fn. Same thing. Difference between Fermi level and intrinsic Fermi level. Okay. All right. Now, so you can calculate phi fp and phi Fn somehow. How can you change phi fp? What is the variable? Notice Na, doping concentration. Okay. Don't look at this equation. If I ask you, just looking at this band diagram, I want to reduce the difference between intrinsic Fermi level and actual Fermi level. What do you do? Who can tell me? How can I reduce the difference between these two levels? Tell me one thing first. Can I change the intrinsic Fermi level anyhow? Intrinsic Fermi level? No. It's basically the midpoint of the band gap. And the band gap is set by the material itself. I have no control over it. So intrinsic Fermi level is set. Only thing that you can change is what? The real Fermi level. How can you change the real Fermi level? By changing the doping level. You can dope it more or less. So if you want to reduce the difference, you want to take this Fermi level up, right? How can you take it up, folks? By doping more or doping less? Less, because if you dope with p-type more, this Fermi level will move closer to the valence band, then the gap will be even bigger. So you dope less. So you can control the doping concentration to change phi fp. See, equations, band diagrams, and concept, they're all telling you the same thing. They're not like independent, okay? All right. All right. Now, what is the other thing? I'm going to show you these equations. We are not going to derive them or anything, obviously. This is the depletion layer width. The depletion layer width matters in a MOSFET. And we calculated the depletion layer width for a for a diode. Remember? Xn plus Xp equals W. Remember, there was an equation. You must have used it for your homeworks as well. So similar, for MOSFET, it's like a one-sided junction, one-sided depletion. The other side is oxide. We don't care. So you can calculate using a similar manner as in a diode. And this is the equation that we end up getting. And look, phi s, the surface potential, showed up in the equation. Okay, if you have more surface potential, you can have more depletion. So just keep that in mind. This might be useful for your maths and stuff. That's why I have these two equations set aside. All right, let's move to the next one. And now I'll introduce the concept of threshold inversion point. If there is one concept that is the most important concept for MOSFET, it would be this one, to understand what is a threshold point. Because by changing threshold, we basically, the MOSFET becomes powerful because of the fact that we could tune its threshold voltage. Okay, that's why it becomes powerful. If there is time, I will give you a couple of examples, but if not, I will just skip. Please pay attention. It's easy if you see while I'm drawing. What is the difference between these two band diagrams, folks? These two. Tell me visibly, what do you see? More bending for the second one. Why is it bending more? We must have applied more voltage to the gate, as we just discussed, right, in the previous slide. So obviously, we have applied more voltage. And what kind of voltage have we applied? Must have been positive, of course. And don't take it to be the crown, like crown jewel. We don't always have to apply positive voltage. Depends on the type of semiconductor. If there is p-type here, you apply positive voltage to deal with electrons. Remember, how do you remember this? You have p-type material. You want to invert it and make what? Make n-type. Who is the king in n-type material? Electron. So you want to invite the electrons to come. How do you invite the electrons to come? By apply positive voltage. Simple. So that's how you know. You don't have to memorize or anything. Okay. So you are trying to invert this guy. Inversion turns on the MOSFET. That's why we are trying to invert it. So you apply positive voltage and heavy positive voltage to bend it so much that now it becomes essentially n-type. Now, let's not stop here. Let's move forward. What if I apply even more voltage beyond this? It has essentially become n-type. Okay. But now, if I keep doing it, what happens then? Can anybody tell me? Can anybody help me draw? Basically, super simple. More bending. Okay, bend even more. But now it's interesting. Can anybody tell me what's going on here? Just look at it. This green zone and the blue overlap. What's going on here at the interface? Can anybody tell me what happened here? Yeah, I just bent more, of course. It was already n-type because the Fermi level was closer to the conduction band. But now the conduction band has gone down the Fermi level. What does that signify? Remember, you should remember. Degenerate n plus, not just n, it's n plus basically. So you have electrons sitting in there readily. You don't have to wait for the electrons to come and pile up. They're always there. It's all good so far. So beyond a certain point, at this point, notice geometrically, this is geometry, pure geometry. This is p-type, sorry, this is n-type, and this is p-type. And there is a measure of how strongly it is n-type and how strongly it is p-type. At this point, this hypothetical point where it is equally n-type at the surface and p-type inside, like there is a perfect balance. Beyond it, the surface keeps becoming more and more and more and more n-type. Does anything change to the p-type side? P-type? No, it just stays as is. Only the surface changes, right? So there is a point where the surface is exactly as much n-type as the body is p-type. Does that make sense to you or no? So apparently this measurement, this section, if this is x, and this section, which is the difference between F Fermi level and valence band, which is y, if x and y are equal, that defines a point where you have perfect balance between the semiconductor, which is an n-type material now at the surface, and p-type inside the body. Still with me? Beyond this balance, what happens? Tell me. I just told you. If you keep applying more and more positive voltage, what happens then? This n-type inversion layer keeps getting stronger and stronger. That's called strong inversion, by the way. And the p-type remains the same. Like here, nothing changes. Okay. So don't you think we should celebrate that point where you have perfect balance and harmony? Right? That point where you have perfect n-type strength at the surface, as much as you have p-type strength inside the body, is called a threshold voltage. Still with me? Okay. Now, I showed you the measurement with respect to the conduction band and Fermi level. Okay. There is another way to measure it. There is another way, which textbook prefers specifically for MOSFET. And I'm going to tell you that. Notice there is a difference between intrinsic Fermi level and actual Fermi level, right? The difference is here. In this side, after the crossover, the difference flips. You see that? There is another way to look at it. Instead of looking at Fermi level and conduction band, Fermi level and valence band, you can keep looking at Fermi level and intrinsic Fermi level, because the intrinsic Fermi level follows the same curvature as the conduction and valence band. Okay. So can I say that if this is X, this is going to be minus X geometrically. So that's where the threshold voltage is. Are you guys still with me? Okay. So if I call it phi FP, because this is p-type material, this will also be phi FP in terms of magnitude. So can I say, can anybody tell me what the surface potential is here? What is the surface potential here? What was surface potential? Amount of bending we get. Just look at it. How much bending have we got? Can anybody give me a expression, mathematical expression? Can I say I have phi FP here and another phi FP here? So 2 phi FP maybe? Is that right? So can I say surface potential phi S is 2 phi FP at the threshold inversion point? Can I say that? Okay. So now in this equation, which gave you the depletion layer width, there was phi S. If I replace phi S equals to phi FP, I will get the depletion layer width at what point? At threshold. Thank you. Yes, at the threshold point. So that's why this T shows up. Depletion layer width at threshold. And notice there is phi FP. Why is there phi FP? Because we replaced phi S with 2 phi FP. Where is the 2? Remember, it had 2 before. Now it's 4 because they were multiplied together, become 4. Okay. So why is this important? Because interestingly, this is the highest depletion width that the MOSFET will give you. Beyond this inversion point, beyond this threshold point, something else happens which I haven't discussed yet. Okay. Still paying attention? So the more positive voltage you apply, the more bending occurs, the deeper the depletion layer becomes, by the way. The depletion layer keeps getting deeper and deeper and deeper. But at some point, at the threshold, it becomes the highest. Beyond the threshold, it no longer increases. Something else happens, and that something else will show up in the next class. But are you guys still with me? Okay. All right. I want to read this. Electron concentration at the surface is the same as the hole concentration in the bulk material. I hope you understand that. This is taken from the textbook, by the way. This condition is known as the threshold inversion point. So I hope you understand that. And remember, I told you that this condition is the threshold inversion point. But what is the threshold voltage? See, the applied gate voltage creating this condition is known as the threshold voltage. So this bending is not the threshold voltage. What is the threshold voltage? Remember, here you applied a gate voltage that led to some oxide voltage, some flat band voltage, and then some surface potential. That gate voltage that led to this perfect balance is called the threshold voltage. Does that make sense? So the threshold voltage which led to this perfect balance is the value of the gate voltage, not the surface potential. Remember that. Why? Because you cannot really control the surface potential manually. All you can do is apply the gate voltage and deal with the losses. You can predict the losses before, but you apply the gate voltage. So threshold voltage is a measure that defines where the MOSFET turns on. And I can tell you what happens after this. After that, you start creating an inversion layer. And instead of having depletion deeper and deeper, you start creating a different type of charge, inversion charge. And we'll see that in the next class, okay? That's why this is so special. At this point, depletion stops and your new mode of operation starts. That's called weak inversion. And then obviously, as you can see, strong inversion, right? Weak and strong, depends on how much positive voltage you apply. So I will stop here and we'll start. Oh, sorry, give me 10 seconds. This is the same concept for N-type material. See, now I can do it. So we did it for P-type. Try looking at it for N-type at home. And if you have confusion, please talk to me. Please do it. Don't let it be, okay? Because this will be in the exam. If I teach P-type, I'll give N-type in the exam. So you have to make sure that you understand that at home. If not, I'm here to help, okay? So we'll start from the next slide in the next lecture. Yeah. Thank you.